second talk of the afternoon, or the last talk maybe in the afternoon.
Yeah, thank you.
Okay, so let me come back to this picture. So it's a picture in H11. So here is the picture. Okay, so this is the isotropic cone. Inside this place you have the Keller cone. Okay, so it's a set. As a set, it's a set of classes of Keller forms. Okay, so I denote with this kind of brackets cohomology classes. So Eric used this kind of brackets for currents of integration. I use this for cohomology classes. Okay, so it's a convex cone. It's contained in the set where u dot u is positive, but this set here has two connected components, one here and one here, and this one chooses one of the connected components. Okay. This set is invariant under the transformation F star, and it's an open convex cone. Okay, so the closure of this is called the Neff cone. And here, the line W lambda is contained in the isotropic cone, so that's W lambda. You have W with eigenvalue 1 over lambda. And as I explained, if you take the orthogonal complement of these two lines, you get two hyperplanes, and the intersection of these two hyperplanes it's a subspace which is contained in the part of H11 where the intersection form is negative definite. Okay, so here the map acts as a rotation, here it acts as a contraction, and here it acts as an expansion. So the multiplicator here is lambda. Okay, so now if I take a Keller class, so a Keller class is somewhere here, and if I apply f star to the n and I divide by lambda to the n, then I get a sequence of points here which converges to a class in W lambda. So what I will do, I will fix a Keller class. So I fix a Keller form. Omega. So these Keller forms correspond to a Hermitian metric, and so to a Riemannian metric on the manifold X. And I can choose, I have to make a normalization. So this class, I will call it theta plus. And here I will choose a class theta minus. And I can assume that just changing theta, omega, and theta minus by a scalar, by multiplication by positive scalars, I can assume that theta plus dot theta minus is 1, theta plus dot omega is 1, and theta minus dot omega is 1. Okay? So this fixes theta plus and theta minus. Okay. And so this property, that the fact that the Keller forms converge when I apply 1 over, so this transformation is here is 1 over lambda f star. The fact that it converges toward a class theta plus, in fact, implies that this class is represented represents the cohomology class of a closed positive current. So let me state it. Okay, so the lemma is there exists a closed positive current T plus on X such that let's say 1 over lambda F star T plus is T plus, and in particular the cohomology class of T plus is equal to theta plus. Okay, I just have to multiply T plus by. Okay, so the proof is, what is the proof? So if you have omega a Kähler form, then you get a current T index omega. So this current acts as follows. So if you take a 2 form alpha, say a 1-1 form alpha, you can define the value of T omega on alpha to be the integral on X of the product between omega and alpha. Okay? This is an example of a closed positive current. It's positive because omega is positive. It corresponds to a Hermitian metric. And it's closed because omega is closed by definition of a Kähler form. So now if you apply 1 over lambda to the n Fn star T omega, you get a sequence of currents Tn. All of them are closed and positive because F is holomorphic. But this sequence of currents, if you look at their cohomology classes, you know that the sequence converges to theta plus up to some scalar multiple. So the mass of Tn, which is, so the mass was defined this morning by Eric. It's the value of Tn on the Kähler form, omega. Okay, so it's. But this mass, you can compute this mass in cohomology. And since the sequence converges in cohomology, you know that the mass is bounded. Okay. Now a sequence of closed positive currents with bounded, with uniformly bounded masses, it's a compact, it's a pre-compact space. You can take converging subsequences. It's like for a probability measure on a compact space. If you have a compact space X and you have a sequence of probability measures, you can extract a converging subsequence. Okay? So I can take limits if I take a subsequence. And this provides an invariant current. I mean, this provides a current T plus with the same class theta plus. And if I average when I take limits, so I take average of that, the limit is invariant. Okay, so Dennis, you just arrived. So what I'm doing, I take X is it's an automorphism of a complex projective surface. Okay, and if you use Hodge-index theorem and you look at the action on H11 of X, what you show is the following picture. So you have a unique. I mean, if the spectral radius is larger than 1, then you have a unique isotropic line corresponding to an eigenvalue larger than 1, which I call lambda. There is another eigenvalue which is 1 over lambda, and all other eigenvalues have modulus 1. Okay. So now you have the Kähler cone, the cone of Kähler classes in H11, which is invariant. And if you apply a 1 over lambda F star, so this linear transformation to a Kähler class, and you iterate, you converge toward the eigenline W lambda. Okay? But now if you do that at the level of, not of cohomology classes, but at the level of currents, what you can show is that theta plus is represented by a closed positive current which is invariant, I mean, which satisfies this equation. Okay, so now I continue. Okay, so the point which is not trivial is the following. So in fact, you can prove a better result. There is a unique T plus, which is a closed positive current, such that the homology, here I work with cohomology, so the cohomology class of T plus is theta plus. So if you fix the class theta plus, you can look at a set of closed positive currents T such that the cohomology class of T is theta plus. Okay, so this set, let's call it C of theta plus. So this set is
This is on the edge of the cone?
yes, so that was the picture. So let me come back.
If it were in the middle, it wouldn't be
If it were inside, it wouldn't be unique, right?
No, of course not. So here, if you take the, let's say you take the convex, take the Kähler cone, it's like that, and theta plus, the class is on the boundary of the, okay. Okay, so this set is it's convex. Okay, because if you take a convex combination of currents satisfying this assumption, then it's stable under convex combination. It's compact. For weak convergences, just because we fix the mass of the current when we fix the cohomology class, and it's invariant under this transformation. And what I am saying is that, in fact, this set is just one point. Okay. So let me sketch the proof when X is a K3 surface. So let me prove this theorem when X is a K3 surface. So what I will use is the following. So I gave an example during the first talk of a K3 surface, and what I explained is that there exists a holomorphic two form omega x, which does not vanish. Okay, on the K3 surface. So now if you pull back omega by f, then it's a new holomorphic two form, which does not vanish also. Okay. So it's just omega x times a holomorphic function phi, which does not vanish. Okay. So a holomorphic function on a compact manifold is constant. So this is a constant. And since f has topological degree 1, the absolute value of this constant is 1. Okay, so this means that the volume form, this volume form is invariant under f. Okay. So now I'll take this convex set. So we have one point T plus the one which is produced by the lemma here. This point is a fixed point of this transformation. So now you take another point T and define some kind of distance between T and T plus as follows. So you write T plus minus T. So the cohomology class of T plus minus T is 0. So you can write it like d bar of some function u. And u, you can choose u, you can normalize u in such a way that the integral of u with respect to this volume is 0. U is defined modulo a harmonic function which has to be constant because x is compact. So u is well-defined modulo addition of a constant. So I normalize the choice in such a way that This is 0. Okay, and then I define the distance between t plus and t to be the L1 norm of u. Okay. Okay, now apply 1 over lambda f star. So it's an affine transformation which preserves this convex set, this compact convex set. And when you apply it here, so this is invariant under the action of 1 over lambda f star. This is transformed into a new point. And the distance, what happens to the distance? So u is transformed in u composed with f divided by lambda. And since the volume is invariant, the normalization is okay. I mean, the choice is good. The integral of u composed with f is 0. But now the L1 norm has been divided by lambda. So with respect to this distance, the transformation 1 over lambda f star, it's a bijection of this, an affine bijection of this convex set, but which is a contraction by lambda. So the convex set is just 1 point. Okay? So in fact, you can use the same kind of ideas for all complex projective surfaces to prove the same theorem. Okay. So now what we get is a very strong result, because you see this cohomology classes is represented by a unique closed positive current. So if you have a sequence of closed positive currents and you know that their cohomology classes are converging toward theta plus, then the sequence converges toward a t plus. Okay. Okay, so for instance, I proved the existence of such a current t plus by first choosing one Kähler form omega, but as a byproduct of the theorem, the limit t plus does not depend on the choice of omega. Another corollary is if you take an algebraic curve, so let's say d in x is an algebraic curve, and you define d with this kind of bracket to be the current of integration on the curve d, so it's just the integral on d, then 1 over lambda to the n fn star d converges toward a constant times t plus. Okay. And the constant is positive. For instance, one way to get that is when the self-intersection of d is positive. So it's exactly the same kind of result as the results proved by Eric Bedford this morning, okay, for algebraic curves. Somehow it's easier to prove here. Okay. Okay, so now I want to discuss periodic points. So let's say it's 4. Okay, periodic points. So I want to discuss periodic points during a few minutes, and then I will come back to these currents and give another construction of the same current. But so first periodic point. So why do we expect? So we have the Lefschetz fixed point formula. Okay, so the Lefschetz fixed point formula says that the sum of indices at fixed points of f to the n is equal to the Lefschetz number, which is the alternate sum with alternate signs of the traces of Fn star on the cohomology groups. Okay, and this grows like lambda to the n. Okay, so we expect this sum to grow like, we know that the sum grows like to lambda to the n. Okay, so the point is that the indices, if you fix one point and you look at the sequence of indices of f to the n at the point P, which is fixed, when n varies, this sequence is bounded. And this is not difficult to show for holomorphic mappings, and it's due to Schubin for general diffeomorphisms of compact of varieties. The index is a multiplicity of the intersection of the graph of Fn with the diagonal at P. Okay. Okay. It's a multiplicity of intersection of the graph of F to the n with the diagonal at the point PP.
F is just a map of some degree.
F is, yeah. It's an automorphism for a surface.
It's an automorphism.
Yeah, it's an automorphism. So it's a diffeomorphism on the surface. It's a diffeomorphism, holomorphic diffeomorphism of a compact complex surface. Okay, so what we expect is that the number of periodic points of period n, or dividing n, behaves like lambda to the n. Okay. So there is one issue with this formula. So, for instance, it could happen that the set of fixed points is not, that there are non-isolated fixed points. So you could have curves of periodic points. Okay, let me come back to the picture that I had here, I think. Okay. You see if I
Violate this first theorem.
No, because let me explain. Okay, the first theorem is this converges to the constant times t plus. The constant can be 0, and it's positive if the self-intersection is positive. Okay.
The self-intersection was 0.
Yeah, exactly. Yeah, it's negative. So what happens is in the picture is here. So if you have a curve which is periodic, so let's say C is a curve, it's periodic, so it's an irreducible curve, and then you have C, f of C, up to fk of C, which is C. Okay, then you take the, let's say, the cohomology class corresponding to this curve, and you get a finite orbit in H11. Okay, so you get a finite orbit. So the orbit has to be contained in this space. Okay, C is an eigenvector, and the cohomology class is an eigenvector of f star to the k, with eigenvalue 1. It has to be orthogonal to this one, which has eigenvalue theta minus, and to this one, which has eigenvalue theta plus, with respect to the intersection form. So it has to be here. Okay, so C and the orbit of C is in this space, where the intersection form is negative definite. So this implies that on the orbit of C, the intersection form is negative definite, and by Grauert-Mumford theorem, you can contract C. Okay.
Contract what?
You can contract C, f of C, and all the curves in this orbit. So I mean that there is a holomorphic map from the surface X toward the singular surface X0, which contracts this orbit to a finite set. So the set. So the lemma is the following. There exists pi from X to X naught, which is a holomorphic birational map. So this one can be singular. And an automorphism, let's say f naught of x naught, such that, so first, the diagram is commutative, so we get pi composed with f is just f naught composed with pi. And f naught has no periodic curve. So all periodic curves of f are contracted by pi. So if you want, I mean, if you are not afraid to work on singular surfaces, you can assume that there is no periodic point, okay? Periodic curve.
So you've been telling us the proof of this method, right?
Yes, yes. So the proof is the following: it's that the periodic curves, the classes of all periodic curves are contained in this space where the intersection form is positive definite. Is negative definite. And then you have a criterion which is known as Grout-Mumford criterion, and which says that in that case you can contract separately.
So this lemma is in this four-dimensional, two-dimensional complex set.
Yes, yes. So now I assume that there is no a periodic curve. And I still assume that X is smooth because I don't want to discuss singularities of surfaces. Okay. So what do I want to say?
Sorry, are you still assuming that lambda has absolute value of more than 1, right?
Yes, yes, yes.
Because if not, you can't have.
Yeah, so one comment on this. Okay, so you take an automorphism of say a complex projective surface, and you look at the action on the cohomology. If the spectral radius, so that's lambda, if the spectral radius of this action is equal to 1, then you have two cases. So the first case is when an iterate of f is isotopic to the identity. Or if you prefer, there is a non-trivial iterate of f which is in the connected component of the group of automorphisms. Okay. So the examples are translations on tori or linear projective transformations of P3. Okay. Well, there are other examples, but the most interesting one are these two. Or it may happen that the action on cohomology has spectral radius equal to 1, but you have a non-trivial Jordan block, and the growth is polynomial. Instead of being exponential, all eigenvalues are modulus 1, but the growth is polynomial. In this case, so Gizzatulin and I, we proved that the map, the diffeomorphism preserves vibration on the surface, and the fibers are genus 1 curves. You may have singular fibers, but so it's like a Dan twist on a real surface. And then the growth of f to the n on the cohomology, it's like n squared. Okay. And so you understand everything when lambda is 1. Okay, the dynamics is simple to describe. Okay, so let me come back to this story about periodic points. No, because they are all contained in the same space. So when you contract, you can contract them in one. So as a corollary of this Garrett-Mumford criterion, you get that there is just a finite number of periodic curves. Okay, and then if I come back to this theorem that I erased, I think, this one. So now if I remove, if I assume that there is no periodic curve, then this is like that for all curves. Okay? Okay. Okay, so what can you do with this kind of arguments and this kind and algebraic geometry? So the best theorem that I know is that the number of...
How did you get down to the absolute value is 1 over here? At the periodic point, and then what? You got down to the periodic points, and then you said something about, you said when the spectral radius was 1, I don't know.
So I said something that I don't want to explain during 10 minutes. So I said that when the spectral radius on the homology is not 1, then we can describe the dynamics.
Okay.
Okay. Either it's like a translation on the torus, or it's like PGL3 acting on P2, or it's like a Dehn twist with respect to an elliptic vibration. But I don't want to describe this. But I want to keep...
If it is 1.
If it is 1. Now I come back to the lambda because
You
of
haven't
it.
done this case yet.
Yes, I'm in this case.
Okay.
Okay. So here, what you can do when you look at this Lefschetz formula, you can prove that there is an infinite number of periodic points. You can prove that the periodic points are Zariski dense. And in fact, this statement works over any algebraically closed field, even in positive characteristic. You can also prove that there are orbits which are Zariski dense, but not much. Okay. So now I state a theorem which is a consequence of the work of Cantat, and which uses Pessin theory. So it's a direct corollary of what Cantat did. So the number of periodic saddle points of period n grows like so lambda to the n. So in fact, it goes like and for all small epsilon. Okay, so it's not an asymptotic behavior; it's a lower bound. Okay, so let me recall what saddle point means. It means that so the point is periodic, so it's fixed by an iterate of the transformation, and the differential of the iterate at the point P has one eigenvalue which is smaller than 1 and another which is larger than 1. Okay. So from this theorem, we know that there is an infinite number of saddle points. So let me pick such a saddle point and describe the construction which is a new construction of the same current T plus. So let's say it's 5. It's what I call all-force currents. Okay, so you take for simplicity, assume that P is a fixed point. Okay, so the differential of the map, there is one eigenvalue which is larger than 1, and another which is smaller than 1. And so we have this stable manifold. So locally, if I take a small ball around the point, I take the stable manifold and I take the intersection and the connected components which contain the point, it looks like a disk. Okay, so since everything is holomorphic, it's like a holomorphic disk. And the stable manifold is a union. So this one is the unstable manifold. So the unstable manifold is the union of all images of this disk by the forward iterates of f. Okay, so it's a Riemann surface. It's a union, an increasing union of disks. So it's a simply connected Riemann surface. And the transformation f induces an automorphism of this Riemann surface, which fixes the point P in the middle. And the differential at P is beta, which is larger than 1. Okay. So this surface cannot be a disk. It has to be a complex line C, because automorphisms of disks are isometries. So this is parametrized. So let me draw the stable manifold like that. So in fact, it comes back here. So as Eric explained, there exists a map, an entire curve C into X, so P corresponding to the unstable manifold. P is a parametrization. So it's a one-to-one map onto the the unstable manifold. Okay. Now, given a non-constant entire curve, so a holomorphic curve like that, I can construct closed positive currents. So that's what Alfors did. I mean, Alfors, Nevenlina, and other people. So here is the following. So you take, the construction is the following. So you take an entire curve. Non-constant. You take the disk of radius r. You take the image of this disk. So you get a disk in X. And you can compute the area of the disk. So I have a Keller form which is fixed, and I use this metric. So the area with respect to omega, let me denote this by A of R. And you can compute the length of the boundary. Okay, and then you can look at the current of integration on the disk of radius r. So you define, let's say, T of r to be the current of integration. Okay. So this current is positive because you integrate on a Riemann surface. It's not closed. I mean, take the derivative, what you get is the integration on the boundary. Okay. And when the radius goes to infinity, of course, the mass of this current goes to infinity, I mean, because you get larger and larger disks. So you normalize by the area. Okay. What I say is that there is a sequence of radii such that at the limit, the length becomes negligible with respect to the area. So at the limit, you get positive currents. So let me show that. Okay, so I want to show that I can find a sequence such that at the limit the current is closed, so such that the length of the boundary divided by the area, the normalization, goes to 0. Okay, I want to show that such a sequence exists. So if not, so the length of R divided by the area is uniformly bounded from below, and I want to contradict this this property. So it's not hard. It's a Cauchy-Schwarz formula. So I try to do it. So what is the area of the radius R? So you parameterize the disk. So it's integral between 0 and R. 2 pi. Okay, so that's the area. So here the norm is in fact the length of this vector with respect to the Keller form. Okay. The length is just the integral Exactly, so you apply Cauchy-Schwarz, okay? let me do it. Okay, I like to. Okay, so do it. So let me do one computation. So if you take the derivative of A with respect to R, oh yes, with respect to R, you take 2 pi. And there is no D. Okay, so it's C prime at R square. So the square of the length is bounded from above by, so let's say integral 0 to pi square it's less than 2 pi r, and I put 1 r here, and okay. So now if this is bounded from below, you divide everything by the square of the area. So you get a lower bound. Because here I have L to the square, and my assumption is L over A, okay? So I just take the square of the assumption above, and I plug in this here. So I get okay. So now you divide by R, and you integrate between 0, I mean, let's say, between 1 and capital R. Okay, you get something like log of R, which is not bounded. And here you integrate this between 1 and R, and you get 1 over A minus 1 over A capital R. And this is bounded. Okay, so you get a contradiction. Okay, so this means that this assumption was not satisfied, and there are sequences such that the limit, such that the boundary becomes smaller and smaller and goes to 0 with respect to the area.
You're assuming the area is infinite?
No, here I'm not assuming that the area is infinite. Okay, so I will state a theorem which, to prove it, I need to average in a different way. So I put, let's say, B of R, it's just the, you integrate between T is 0 and T is R, A of T dt over T. Okay, so it's a logarithmic average. And then you replace T of R by S of R. It's B of R. You do the same here. 0 R. So it's just a logarithmic average of what I did before. Okay. And the theorem is the following. So I assume that I have an entire curve. So let C a non-constant entire curve in let's say complex projective surface. Okay, so first, if the area is bounded, then C is contained in a rational curve. So it's a curve which is isomorphic to P1. It may be singular, but next. 2, if C is contained in an entire curve, in an algebraic curve, then of course the genus of E is 0 or 1, and this sequence of currents converges towards the integration over the curve E. So S converges toward the current of integration of E up to some non-zero constant. Okay, I mean it's E divided by the area of E. Okay, so what the interesting point is when the area is not bounded. Then there are an all closed positive currents T, which are limits along a subsequence of S. Okay, so there are such currents by the previous argument. All these currents satisfy the following property. So you have a closed positive current. You can look at its cohomology class, and you can intersect it with an algebraic curve D. And this is always positive, I mean non-negative for all algebraic curves D. Okay. So this is basically due to Nevanlina, and this comes from the Jensen inequality. That's why I average like that. And this in turn implies that the self-intersection is positive, and T is in the closure of the Keller cone. So that's, you apply what is called the Nakai-Mosheson theorem. Okay, so now I can apply this statement, so I won't prove it. So this is not trivial, but one can. This is basically Jensen inequality, and then Nakai-Mosheson. Okay, so apply this to unstable manifolds. So here you assume that P is a fixed point. It's a saddle fixed point, and you parameterize the unstable manifold. Okay. So you take such a current T, which is given by integration on the curve on this entire curve. Okay. And then you pull back. Oh yes, let's say you push forward T. Okay. So the current T is a limit of current of integrations on larger and larger disks in the unstable manifold. But the action of F in the unstable manifold increases these disks. So at the limit, you have an inequality like that, which means that if I take the value of this current on a positive form, then it's larger than the value of T on this positive form. Okay. Then you use this, That's true for all. And you use this theorem. Okay, so T, the cohomology class of T, in my previous picture, which I erased, has positive self-intersection. So the cohomology class of T is, here you have the convex Keller cone. The cohomology class of T is in the closure of this cone. Okay. And you use this property and you show that, so it's not hard. This implies that T is equal, is contained in W lambda. It's proportional to theta plus. Okay, so I don't have time to do it, so I want to say something after that. So it's just playing with this picture and this inequality. Okay. And by the fact that theta plus is represented by a unique closed positive current, you get that T is equal to T plus modulo some positive constant. Okay. So what I sketched is a proof of the fact that all so here is a statement. So it's a theorem which is the following. If P is a saddle periodic point, and T is such a current, so it's a what I call an all-force current determined by the so I made a mistake here because it's F lower star, so here it's T minus, I guess. Yeah. Then T is proportional to T plus. Okay, so to apply this theorem, I need to rule out the possibility that the curve is contained in an algebraic curve. And this, I took care of that a few minutes ago by removing all periodic curves. Okay, I have removed all algebraic periodic curves, so this is ruled out, and I can apply that. So what is good with the current T plus, no, T minus, yeah, is the following. So let me summarize what I did. So what I did is I looked at the action on the cohomology on H11. I explained that just by using Hodge index theorem and linear algebra, there is a well-defined ray W lambda here. So this is given by the complex structure, by the geometry. Okay. Then I explained that if I fix the class theta plus here, there is a unique closed positive current which represents this class theta plus. So it's completely determined by the complex structure. Okay, it's unique. And the good point is that this current T plus is given by all stable manifolds, okay, of all periodic points. So if you take a saddle periodic point, you look at the stable manifolds and you get T plus. Okay. Okay. So the last point that I want to.
If the support of the current doesn't pass through the periodic point.
Say it again.
Yes. The current. It's at infinity in the unstable manifold. The current.
Yeah, I will state that in, I guess, 3 minutes. Okay. So one thing that I didn't do, I didn't explain if I come back to Eric's talk, so and Misha's talk. So in their talk there was a function, the green function, okay, such that the current for the Henon mappings or for one-dimensional I mean, for polynomial in one variable, the current, so Eric had a current mu plus, which is my t plus, is dd bar of the green function. Okay. So here I have no global green function. But locally, I can write the current t plus as dd bar of some function. And these functions, it's not hard to prove that they are Hölder continuous. So I can take the product of t plus and t minus. Okay, so I guess.
That's all.
T plus and t minus have locally are dd bar of continuous functions, so I can define the product. And that's a measure. And because I normalized with theta plus theta minus equal to 1, this measure is a probability measure. And because t plus is multiplied by lambda and t minus by 1 over lambda, it's invariant. Okay. And the theorem is that this measure describes the. So first, it's a unique measure with maximal entropy, and also it describes the repartition of periodic points. So it's Cantat theorem plus equidistribution. So again, let's do that. The theorem is so first. So Misha explained the definition of entropy for a transformation which preserves a measure. Okay, so the entropy of f with respect to mu is always bounded from above by the topological entropy, and here it's equal to the topological entropy, and this equality characterizes mu. Okay. The second statement is that every saddle periodic point is contained in the support of mu. So this is assuming that there is no periodic curve. Okay, so this is what you had in mind. Okay. And moreover, mu describes a repartition of periodic points. So if you take 1 over number of periodic points of f of period n, you take you put a Dirac mass at p. I mean period dividing n. Okay, so you solve fn of p is equal to p. So I have just a finite number of such periodic points because I am assuming that there is no periodic curve, and this goes when n goes to infinity. This converges toward mu, and most of the points are saddle points. So if you replace periodic points by saddle periodic points, you get the same statement, and you can instead of normalizing by the number, you can normalize by 1 over lambda to the n. So here you can put periodic points or saddle periodic points, and you get the same statement. Okay? So I think I have to stop, and maybe I'll take a few minutes to ask questions. Yes. Oh yes, yes. I forgot that you did not state. Yes. Yeah. So this also holds for Henon maps. Yeah. So for Henon maps, it's automatic that you don't have periodic curves, algebraic periodic curves. Okay, but let me add one comment. So all this story is efficient if you want to describe this kind of results. Let's say it's results which are accessible by a mixture of complex analysis and ergodic theory. As soon as you want to say something on the topology of the dynamics, almost nothing is known. I mean, for instance, in dimension 1, you have a description of Fatou components. Okay.
The description of
Fatou components for
what?
Fatou components
Ah.
for rational transformation of the Riemann sphere. Here, not much is known. So let me put a few questions for K3 surfaces. So let X be a projective K3 surface. So does there exist a projective K3 and an automorphism such that first lambda is bigger than 1, so this is equivalent to positive topological entropy, and 2, the Fatou set of F is not empty. So this we don't know. So if you go into the world of non-projective K3 surfaces, you get Keller K3 surfaces. All of them are compact Keller manifolds. And then Kurt Macmillan constructed an example with a Ziegel ball, a domain which is where the map acts as a rotation. But when the K3 surface is projective, you always have resonances between the eigenvalues. And so it's hard to construct such an example. I don't know whether such an example exists.
Is there any example in the Kähler case where you have a wandering set of positive measures? The Siegel disk would not be, that would be recurrent. So
The preserving measure here.
So in the
This measure is preserved.
for K3 surfaces, there is a
preserved.
yes, it's conservative with respect to a Lebesgue measure, so you don't have this kind of.
Okay.
And here is another question. So take does there exist? So these are two questions. So a pair X F where X is a K3 surface, a projective K3 surface,
That's not bad.
defined over R. Okay, so X is a projective surface, so it's given by a set of equations. And you assume that the coefficients are real numbers. And F is an automorphism of X, that is also defined over R. Okay, so F is given by formulas with real coefficients, such that. So the first question. So X of R is non-empty, and the entropy of F on the real locus is 0, while oh yes, non-empty, of course, while lambda bigger than 1. Okay, so the first question is, can you produce an example of a K3 surface which is defined over the real number? The real part of the surface is a nice real surface, so it's not empty. And the dynamics of F, it has positive entropy on the complex surface, but the dynamics on the real surface has 0 entropy. Okay. Does there exist? Excuse me. I'm tired now. And question Q2 is the opposite. So x of R is not empty, so it's not the opposite. And the topological entropy on the real locus is the same as the topological entropy on the complex locus, so it's log lambda. Okay, so the entropy on the real locus is in between 0 and the entropy on the complex locus. Okay? And there are two extreme cases. So one extreme case is when the entropy is 0, and another is when the entropy coincides with. So this is equivalent to saying that, so modulo this story with periodic curves, this is equivalent to say that all saddle periodic points are contained in the real locus. Okay. And this I don't know. So what I know is that there are examples for which the entropy is as small as you want, but 0 I don't know. Yeah. So that's the kind of question we have. I have no idea how to solve them.
Do you have it as large as you want?
Hmm?
Do you get it as large as you want?
No. I know no example with more than 1/2 here. 1/2, no. I think there may be example with more than 1/2 of them. Okay, so it's already 20 times.
So the dynamics on these for two components would necessarily be Ziegel disk, Ziegel balls?
No, I don't know. No, for instance, I think it could be maybe easier to construct a non-empty Fatou components with the following idea. You start with something which is defined over real numbers, such that the real part of the surface is a torus. Okay, it's a surface of genus 1, and you can try something which is like Hammond rings. So try to construct an example such that the entropy in the real locus is 0, and the map is analytically conjugate to a translation on the torus. And then in the neighborhood of this torus, you may have a Fatou component. Okay. So there are examples like that for birational transformation of rational surfaces. But for I don't know. So I'm not sure that the easiest way to construct a Fatou, non-empty Fatou set is to look at periodic points and Ziegel domains because of these resonances.
The story you don't necessarily have similar resonances, so you can imagine tori without resonances.
Yes, that's right. Yeah.
Other questions? Does any of this go over to the case of general endomorphisms of a compact variety?
You mean in any dimension?
Well, I mean, considering the case of a holomorphic self-map.
Yes, so there is an issue with. So one thing which works in all dimensions is when you have a. So one story which works is when you have a endomorphism such that the topological degree is the largest eigenvalue that you can see on cohomology. So if you assume that the topological degree is strictly larger than all other eigenvalues, then you can prove results which are similar to the one-dimensional case. So there is a unique measure of maximal entropy which describes the repartition of preimages of generic points and also of periodic revealing points. This is true. This is due to Gauge. And the problem is, so one story that I did not explain is, problem is to construct examples. And so that's why I took half an hour at the beginning to construct examples of automorphisms of surfaces. But if you move to higher dimension, all the constructions that I know, except on a billion varieties, they lead to birational transformations, pseudo-automorphisms. And for endomorphisms such that the topological degree is larger than all the other eigenvalues, basically the only example I know is given by projective spaces, abelian varieties, and variation on that. So I think a better question is to try to do these kind of things for rational transformations. There are much more examples in all dimensions, and that's another discussion. Some of this story works under natural but technical assumptions for birational transformations of surfaces. So this is due to Eric and Geoffrey Diller and to Romain Dujardin. But it's more technical. But it's the same kind of ideas. But for instance, I took just 1 minute to say that t plus and t minus are locally dd bar of continuous functions, and for rational transformations, it's a big issue to understand the local potentials and the class of function that we get. Does that answer the question? No.
Other questions? Oh, thanks.